I'm Anil Kumar, and in this video I'm going to discuss how to represent points in space. Now I've seen that many students, even at the end of the course on vectors, really doesn't understand how a point is represented in R3 or three-dimensional space. So before really getting into it, we'll talk about what do we understand by one dimension, two dimension, and three dimension, and then we'll touch upon this topic, right? So now first let me talk about how to represent a point in space. And space we could represent in one dimensional space, two dimensional space, or three dimensional space, right? When I say R2, we're talking about XY plane, two-dimensional space. R3, XYZ plane, like in your room, three-dimensional space, correct? Now let's see first the one-dimensional space. What does it mean? Now when I say 1D, I mean we want to have only one dimension, right? So generally that one dimension could be length, could be distance, something like this, right? Could be time, right? Any one of them taken at any instance, right? So that is one dimension. How do we represent things in one dimension? We represent with the help of a number line. And on a number line, we plot something like this, a straight line, and saying somewhere in between we have a marker, which is kind of our reference, right? So this point is kind of our reference. And from this reference point, which sometimes we call as origin, we measure everything. So anything on this side will be treated as positive, and on the other side will be treated as negative. And it can extend to anywhere from minus infinity to plus infinity. So any point here, if I say this is 1, then this is 2. And on the other side, if this is minus 1, that becomes minus 2. And all points in between, all these points in between, there are infinite points in between, right? So we say they are a set of real numbers. We say they are set of real numbers. So mathematically, we say that if I represent, let us say x, if we say x belongs to set of real numbers. So that's what we say. So any point can be represented. And we say, well, the distance from this point to that point is 2 kilometers on the left or maybe south. And when we say the right side, we normally associate north or east with the right side whenever distance is concerned, right? Time, negative means past, that's future. Okay, so that is how we work with one dimension, correct? Now when we move on to two dimensions, then we are actually talking about what? Now we say 2 is two dimensions, right? So we have two dimensions. Like length and width, right? There are two dimensions, two parameters. We can say two parameters, okay. So since there are two different dimensions at one time, we really need two coordinate planes. Now this is one axis. We normally call this as x-axis. So we add one more axis to it, which you're very familiar with, the name y-axis, correct? And that is the x-axis. So as this goes from negative infinity to positive infinity, the x-axis remains kind of similar. It goes from negative to positive infinity. But we introduce another axis for the second dimension, and it also moves from negative infinity to positive infinity, right? So that is your two dimensions. So any point, let me make here, any point here could be represented as a combination of something along the x-axis. We say, well, you go 2 units along this x-axis, and then you go 1 unit along y. So you reach a point, we say point P, whose coordinates are 2, 1, where this is 2 units and that is 1 unit. Is that okay? Now we could have anything on this side. It could be time, for example, and on the other side it could be distance, for example, right? So anything. Perfect. Now, if I make something what you see here, if I join it kind of like this, you also find kind of a rectangle form, right? So we also treat this as a rectangular coordinate system, right? So from this, and it also has a point of reference which is also called origin, and since we are associating x and y coordinates with every point, here the origin represented by a letter O could be written as 0, 0. Does make sense to you? Correct? So I hope this two-dimensional system is absolutely clear, right? Now you will notice here that as soon as I divide it like this, we get these 4 things here. We call them quadrants. So it's quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So what you also see here is that the value of both x and y are positive here, right? So they are both positive here. On this side, the x value is negative, y is positive. So when you go to quadrant 3, both x and y are negative values, and in quadrant 4, x is positive, however, the y is negative. So these 4 quadrants, you see how the points change. Earlier, you saw that the points could be only negative on the left side and only positive to the right side. So we have 2 sides on this number line which are defined by the origin. So on the left side, if you move, you get to more and more negative points, and on the right side, you see more and more positive points. In a 2-quadrant system, rectangular system, 2-dimensional system, that is how the points are, right? So we call them a rectangular system, coordinate system, 2-dimensional system, x-axis, y-axis. Depending on the dimensions, you can always change their names. You can write time and distance, right? So there are no restrictions. However, the concept is very clear that any point on this paper, for example, can be represented by this kind of system. Okay. Now let's talk about 3D. So what we have seen, what is 1 dimension, 2 dimension, and now we'll get to 3 dimensions. So 1 dimension, we had a line like this, right? So, and when we took to 2 dimension, we introduced a vertical line. Let me show it here like this. Now, in each of these, we always have a reference point which we represent by letter O, and it is called origin, right? So that's a common name and is always called origin. And everything is seen with respect to this origin in our coordinate system. Perfect. You see that all these lines extend from minus infinity to plus infinity, and when we added another line that also extends from minus to plus infinity, and the line which we introduced was at right angles, right? Now, so that gives you an idea that when we move into the space, then it is addition of 1 more dimensions, right? So what happens now is that we already have this system with us, which is the rectangular coordinate system. Since every point is being represented by a rectangle, we now introduce you another dimension, so I need something else, right? So we introduce the 3rd line here. Again, going through the origin, right? Again, going through the origin. Now, naming becomes slightly different. Here, we had just a number line. We never named it, right? But we said x and y because there are 2 different things here. Now here what we say is we want to keep the plane of the paper as our basic xy. So we call this as x, this as y, right? And this one as a z-axis. So we have introduced another axis with all the lines which are perpendicular to one another, right? So what you see here is something like this, that this particular line which doesn't seem to be perpendicular, but see, now it will look like perpendicular. XY plane is perpendicular to one another. This is also perpendicular, right? So we have all perpendicular axes. So x-axis, y-axis, and z-axis. And in our R3, which I have just shown here, the idea of taking one side as positive, the other as negative, so these sides are termed positive, comes from the right hand rule. So we follow a right hand rule. That is to say that if I hold something on my right hand, thumb points upwards towards the z-axis, right? So it's kind of like that. So that is how R3 comes into picture. Okay, so now what I will do here is I'll again draw the same thing, but with their positive axis, right? So I'll draw the same thing with their positive axis. So let me begin with x-axis. So I say, well, this is my x-axis, right? So positive this side, and I'm saying that is my y-axis, positive towards the right. And then I have a z-axis which is positive going upwards. So that becomes R3, a space representing the space. It could be correlated with corner of your room. So these are the walls just in front of you on the left side, right? And that's the floor which you look at. Now here, any point could be represented. So let me show you how to represent points in this particular plane. So the first point of our interest is the origin itself, which we say O, and this point we'll always write this as 0, 0, 0. That means along the x it is 0, along the y it is 0, along the z it is 0. Just that point. Do you see that? Okay. Now, if I denote these as my 1, 2, 3 markers on x-axis, let us say, right? So let me just... So every number line, for example, has a scale. So that is the scale which I have made. Now look into some points. For example, on x-axis, if I move 1, 2, 3 units, for example, and reach a point, this particular point here will be a point on x-axis, correct? And the coordinates will be, since I moved only 3 units along the x, and I did not move along y and z, 0 for them. 3, 0, 0 represents a point on the axis, x-axis, right? Do you see that? So that represents x-axis point. So the location of position is on the axis. So I'm saying this point as, let us say, A, right? So the position of A, we will say, A is on the x-axis. Do you see that? Now, if I have to represent a point on the z-axis, I could say, well, the position is, let's say 2, right? So I'm moving only 2 units up. So that particular position, let me call this as B, for example. Okay, so it doesn't matter. Let's call this as B. So the point B will be 0, 0, because we did not move along x and y, and this will be 2. So what you note here is that in this R3 system of space, every point is represented by A, B, and C, where these coordinates are. How far are you from the origin in these directions, x, y, and z? So they represents directions, position, movement along x, y, and z axis respectively. Do you understand? So that is what the link is. We'll call them with some direction associated numbers also later in vectors, but I don't want to complicate it here. Okay, so what I've shown you here is points or the position on the axis. Similarly, we could actually represent a position on a plane. For example, if I move from this point to another point which is along the y-axis from here, for example, then let us say I move 2 units to the y-axis right side. Okay, so I go here 1, so that is 1, is it okay, and 2, so I'm going 2 units, is it okay? Now this particular point, let me call this point as C. To reach C, I first moved along the x-axis 3 units, then along the y-axis 2 units, and didn't move anything along z-axis. What you see here is, if I complete this parallelogram, do you see this parallelogram? So the position C, the point C is on xy plane. Do you see that? So this is on xy plane, the point C. So if the coordinates for z are 0, that means we are on xy plane. I hope you get it, right? Now, if I have a coordinate 2 units up from here, for example, if I move up 2 units from y to this place, in that case, coordinates of this point will be what? I did not move along x, so that is 0, 2 along y, and 2 along z. So that becomes the coordinate for the point which is represented here. So you see all the movement is taken care of from a reference point origin O. You get an idea, correct? So that is how we represent our points in space. Now what we have talked about is the point C, which is in xy plane. Now can you tell me in which plane is point 0, 2, 2? Clearly, it is in YZ plane, right? So it is in YZ plane, correct? So in YZ plane, we have the point 0, 2, 2. Perfect. So the coordinate value for x is 0. That means we're talking about YZ plane. If the coordinate value of 2 of them is 0, then we are on an axis, correct? Now, if we are not on the axis and a plane, how do I represent a point? Well, here is how we can do it. Think about the same point we started with, origin, moving 3 units towards positive x-axis, 2 units towards y, and then again 2 units up. So when I reach this point 2 units up, let me call this point as the point D, right? So let's call this point as point D. Point D here will be represented by the coordinate 3 along x, 2 along y, and 2 along z. So that is in 3-dimensional space. So I hope you are getting the idea, right? So what I'm doing now is that I'm going to complete a figure which will give you a box type of a look, and that will help you to understand how we actually represent points in our space. Do you see this box? Perfect. So this point here is point D, and if I connect it with the origin, that with an arrow, it becomes position of D in space. So what we see here is position of D, which is 3, 2, 2. All are positive. Do you see that all these are positive? You will also observe that this particular box seems to be lying on the right side and above this xy plane. Do you see that? And in front of us, right? So what we do here is we also appreciate that this type of a coordinate system divides the whole space into 8 parts. So this coordinate system divides into 8 parts, and these 8 parts are called octants. And if all are positive, this is called the first octant. The others, we don't have any particular criteria. As we saw here, any point on the left is negative, on the right is positive. Here we say we have quadrants 1, 2, and 3 and 4, where the points are positive, positive. Here the points are negative, positive. Here the points are both negative. And here we have a positive and negative coordinate. Now that is 4 quadrants. Here, what do we have? Here we have 8 quadrants. And how do we define them? Based on x, y, z, right? So they are defined. Now I'm writing x, y, z. Let's say lowercase x, y, z. Is it okay? So on the x, we decide left or right. So on the x, we decide whether it is on the left side or on the right side. Is it okay? So if x is positive, it is right. So positive is right and negative is left for x. If we are talking about y, I'm sorry, x is like front and back. I'm sorry. So, okay, I'll not erase this, but I'll extend this to y. Sorry. So y is left and right. So y is left and right. If I go negative, I'm going left side, and right side is y. Okay. And right is positive for y. Now for x, actually it is front and bottom, right? So let's for x, we are saying coming front positive, right? So this is front is positive x and back is negative x. Is it okay? So front x is positive and this is back negative. As far as z is concerned, going with my color code, which I've tried to maintain here a bit. For z, if it is positive, we are on top, right? So for positive, it is top, and for negative, it is bottom. Do you see that, right? So that is how x, y, z, and these combinations, 2 and 2 makes it 8 combinations, right? So how do we get 8 out of these 6? That is also a troublesome thing to understand. It is 2 to the power of 3, right? So these are the total number of combinations you could have. You could have bottom, back, left. You could have left, front, top, left, front, bottom, like this. If you make, you get 2 to the power of 3, which are 8 combinations. Does make sense to you, right? So we say any point in this particular space could be described with the help of octants, and that's what it is. So if I have a point, let us say, let me just write down a point here. Let's say point P is 2 minus 3, 4. In which octant will it be? Since this 2 is positive, we say it is in front, right? So I'm writing F for front. And this minus means left, so front left. And 4 means top, FLT. Do you see that? Front, left, and top. If I write a point 2, which is kind of, let's say, 1, let's say minus, right? 2 and minus 5. So that minus will make me move backwards. So it will be back side, right? And 2 means on the right side. And minus 5 means bottom. So below or bottom, let's say B, right? So bottom. So that could be the way of describing the octants for any particular position. So I hope that makes sense, correct? So in R3, we describe position in terms of octants or whether it is on origin. So there are a few terms which you could use. One, you could say the point is at origin. That is point O, right? It is on axis. It could be on any axis, X, Y, or Z. Or it could be on a plane, XY plane as we saw, right? YZ plane we saw. Or it could be in an octant. So we say octants, which are 8 in numbers. Remember that. If all are positive, it is octant number 1. So this is octant number 1. For the others, we don't have a number. So all of the 7 are described with the terms like left, right, back, front, bottom, or top. Perfect. So I hope that gives you a fairly good idea about representing and describing the position of any point in R3 or space or 3 dimension. Feel free to write your comments, share your views, and I hope I could make it understandable. I'll provide you with some context which will give you examples to work with. I hope that helps, and all the best. Thank you.